And so we're back streaming again. We just finished up, I think, using energy with rotation for swinging motion. I now want to look at page 75. Okay, and I'm going to start screen sharing. We're going to talk about problems with pulleys and blocks, but rotation now. Let me get into it. All right. So here we have a color version, I think, of what's in your book. So we're going to look at these types of problems now, and we can handle these with both torque or energy, but let's first just get our basics down. Now, in this case, the pulley's not moving up and down. So I'm starting right here. We have a pulley, and so I don't need to worry about gravitational potential energy or translational kinetic energy for the pulley. Again, the pulley is rotating, so there's an omega, but it's not translating. It's not going from point A to point B. Translating is going somewhere in space. Here, the center of mass of the pulley, to be clear, we're talking about the pulley, is not moving. All right. Now, the blocks are not rotating. So for the blocks, we don't need to worry about rotational kinetic energy. All right. So we need rotational for the pulley. We need translation for the blocks. In this case, and in most cases, we're up to this bullet now, there's tension in the string, but it's working upwards on the purple block and downwards on the pulley. Similarly, we get a tension that's upwards on the red block, but downwards on the pulley. Okay, so in this case, there's tension is an internal force. It does no net work. So that's cool. We don't need to worry about the tension in our energy equation. Unless otherwise specified, we're going to ignore axial friction. Okay, otherwise that's something there. And then something that's kind of nasty in these problems that we have to think about, arc length. So the arc length of string unraveled from the pulley, that's the same thing as saying the length of string unraveled, but I like to think of it as an arc length because think about it, this string is wrapped around the pulley over and over and over again. And so as this block pulls down, it's going to unravel a certain arc length. And this is one of the reasons why we don't want to say every 2 pi radians reset the angle, because it's going to matter whether you do 1 revolution, 2 revolution, or 3 revolution. All right, I think that's, let's do one more. Yeah, all right. Okay, so going back to here, the arc length of string unraveled is typically equal to the height displaced by the blocks. This assumes that the strings do not slip on the pulley. So if you see me say something about that, if you hear me say the strings don't slip, that's my way of saying, oh, well, this arc length is the same as this distance here. So if I could unravel this height that this one falls is probably going to be equal to about that much string maybe. So it's saying that this arc length is the same as that red arrow. And to reinforce this for the other one, right? This one falls a much smaller distance because it's on a smaller radius. We see now the horror of these problems. That one only covers that much arc length. All right, hopefully that's about the same. That's what it's supposed to be. So my apologies if that's not perfect. They should cover, this goes, we said earlier, these two should have the same arc length, the same number of radians of string unraveled, but they have different amounts. So they both have strings can are equal, but the angular quantities are equal. Something important to recognize here, when you have these problems, because angular quantities are all the same, it's often convenient to solve the problems for angular quantities, then read the problem and say, do I need a velocity instead of an angular velocity? And I'm going to check the chat because I see there's some action there. All right. Okay. Hopefully the audio is back now. All right. So the change in the height of the block is still 2 pi times the radius. Absolutely not. So it's close to that, but 2 pi is a special value of theta. S equals R. I'm writing it in the chat. Oops. So let me see if that makes some sense. If it rotates exactly 2 pi, then you would be right. But really, it is the radius times the change in angle. So it could be like pi or pi over 2. Is that pretty good, Ryan? If so, just dump that in there. Okay. All right, sounds good. Let's move on. All right. All right. Hey, we're not going to understand this. Oh, there's one more chat. Let me see. Okay. Oh yeah. So let's do a problem so we can understand what this crap means. But I just wanted to point this out. All right. Let's go look at an equation here. All right. Finally, we're up to something. I've been telling you since the beginning of the semester. Someday we would do a problem where there's a mass. Now, if you recall from earlier in the semester, this was the acceleration of an Atwood's machine, and there was one tension. It turns out this is now tension 1, and this is tension 2. They are not the same anymore, even if it is the same string. Think about that. The tension on opposite sides of the pulley are not the same. This is really hard to show you over the internet, but let me put it to you this way. There's some friction right here at the edge, okay, all along that squiggly red line. That friction is actually connecting the string to the pulley. Now, we don't say connecting. The word we should be using is called coupling. So there's friction which couples the string to the pulley. But that friction on this point right here does zero work. Why? Because the friction that allows the string to couple to the pulley does not displace the string relative to the pulley. All right, that's a lot to digest. One more time. The friction which couples the string to the pulley, which prevents the string from slipping on the pulley, is required to make the pulley turn. Okay, so that force has to be there. However, it doesn't do any work. So that friction doesn't show up in our energy problems, but it will cause a difference in tension from one side of the string to the other. Trippy, eh? All right, enough on that. Let's get into here and look at this problem and see how we handle it. All right. Whoops. Let me clear my annotations first. So I'm going to look at the solution to 10.52. Everybody read 10.52 really quick. I'm going to read it as well. See if there's anything else I need to say. Okay. We have a non-negligible mass pulley. If you see a pulley with negligible mass, you don't need to worry about this crap. But now in chapter 10, how do you handle a pulley with mass? Axial friction is still negligible, but now there's a moment of inertia, right? About this axis. Okay, and the moment of inertia is I. The tension differs. This is totally different now. The string is still massless and inextensible. The string does not slip on the pulley. This is really important. Because the string does not slip, we can use this equation. If the string slips, we can't use that equation. String does not slip. That's what allows this. All right. Now I'm going to go pop into the solution and take a look at it. All right. Get this thing out of here for a second. Whoops. Let's start right here. If you get used to this procedure, it will become quick. If you don't, this is either going to be on the midterm 2 or the final or something with these. These I love these problems because you have to do forces, you have to do torques, you have to do moment of inertia. So you're going to have something where you have a swinging motion or a torque like this. So you got to get good at these. So take the time to just hammer these out, learn the tricks. All right, here we go. There's the purple block. So just showing you one last time, I want to make sure you understand this one is the purple block right here. M1 is purple, and I think this two, M2 was red, okay? So now when I go over and show you the solutions, this was the purple block, this was the red block, and right here in the middle is the pulley. All right. FBD is pretty straightforward. Force equation, pretty boring. Go over to the red block. It's pretty straightforward. So that part shouldn't be any different. There is one significant difference. Even though they're the same string, now they're called tension 1 and tension 2 because of all that friction coupling crap I was talking about. Good enough. All right. So now in this case, what are the forces on the rotating object? All right. Well, this is the force holding up. It's the pivot, right? Holding this thing up. That doesn't cause a torque, but it is there. What about the weight of that pulley? It totally exists, but neither of these two blue forces here in the middle do anything as far as the torque is concerned, right? Because each of these have a line of action through the pivot point, neither one of these causes a torque. We do not need to worry about those things causing a torque. All right. So all right. In this case, all right, there is the lever arm for this one. Sorry, it's interesting. I can hear my kids getting scolded in the background for wasting food during the pandemic, so it's distracting me. Kids, what are you going to do? All right. Anyways, this is radius R. Over here, this is radius R. And so, and again, because of these two angles being right, there's a sine of 90 degrees here, which sine of 90 degrees is equal to 1. And there's similar for right there on the purple one. So there's a similar sine of 90 degrees right there. All right, so both of those things, that makes sense. Let's see if that torque equation makes sense. Make sure you understand this part right here. That's the new thing. All right. And you can ask me questions after we're done. Because the string doesn't slip, I can use this fact. Oh, sweet. That allows me to take this junk and switch it out. You see that? Now, hey, everybody, check this out. Look at this important thing, okay? Notice this has got A in it. This has got A in it, and this has got A in it. Those are all the same. That is the magnitude of translational acceleration of the blocks. Because they are connected by the same string at the same radius, they have the same A. All right, that's important. Well, now we've got an equation with A in it, another equation with A in it, and a third equation with A in it. I'm going to stack those equations. Oh, and this one is a convenient trick. If you divide by R, this is going to make things look pretty. You'll see in just a second just how pretty this makes it. Okay. Okay. Here we go. This is the same stack and atom trick where if you remembered to divide by R and get units of force, this becomes a very fast problem. If not, it's going to suck for you on exam day. If you don't do this trick, it will suck for you either on test 2 or the final or both, okay? So it's one of these is coming at least once, if not twice, right? So once you see this trick, look at this. T1 drops out. T2 drops out. The left side is super easy. If you don't know this trick, it becomes cumbersome and boring and long. Now look at this. This is the mass of block 2. Mass of block 1. This has units of mass. I is usually something like 1/2 mr squared or 2/5 mr squared or something that's an mr squared, right? So the r squareds will drop out. This has units of kilograms. That right there has units of kilograms. So this is now our new effective total mass, where we use some of the rotating mass depending on the type of shape you use and the mass distribution you use. And once you do that, this looks exactly like before. If M3 was equal to 0, I would equal 0, this would equal 0, and we get back a standards Atwood machine. I'm going to pause there. Isn't that cool? I hope you think that's cool. All right. So in regards to, so once you get a system like this, there's usually some weight force that is going to cause this thing to spin, and you can account for that. Since I don't see anything there, I want to pop back in and keep going. Let's see what we just did. We just found this result. Cool. Now verify we did that, and then determine each tension. This is extremely boring, but yeah. All right, so let's go do it because now we've done all the hard work. Let's just go look. All I did was back sub. So right, tension, let's see, tension 2 right here, right? Well, once I know what A is, I could take this A, plug it into here, and shift this over and solve for T2. It's pretty boring, but it could be done. And you get this result. You should do it, not me. Just check your algebra really quick. All right. And there's T1. Again, I did the same thing. I just shoved it in, solved for T1. An interesting result is if you set I equal to 0, look, this term drops out, this term drops out. We better get the same tension, right? Well, this term drops out, this term drops out. We get 2m1, m2g. Yes, that matches. All right. So it actually does work out if you want to check that. All right. That's pretty cool. Oh, yeah. Okay, so that was using the torque method. Now, even though this is really boring right now, it's important that we see you could do the same thing with energy, and I want to show you that. So look at 1053. It's doing the same problem, but showing you how to do it with energy. I just did it with free body diagrams and torque. Let's do it again with energy. So I'll screen share so you can see what I'm talking about. Reconsider the same problem using energy and kinematics. Wait a minute. Can we use kinematics? Haven't I been saying all day that we can't use kinematics because alpha is not constant? Are we going to run into trouble here? Of course we're not, but think, what's different now in this problem versus all the ones all day? I've been hammering. Don't use kinematics when it's swinging motion, because as the thing swings, the torque due to gravity changes. In this problem, if these blocks are connected by a string and they're accelerating with constant rates, blah, 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 we have a situation here where the torques are not changing because this one is being applied right here. This one's being applied right here. And we expect this thing is rotating this way, but the center of mass isn't changing. It's not Yeah, it's staying right there in the middle, right? So with this particular case, we don't need to worry about alpha being non-constant. This one should actually accelerate at a constant rate. That's why we can do this problem with energy and kinematics. It's very, very swinging motion, I think, is the only one where you can't use that kinematics. All right, I've said that enough times today. I'm stopping that. All right, let's get to it here. Reconsider. Oh, part A. Oh my gosh. So what assumptions do we make in order to assume the acceleration of the system is constant? Well, that is somewhere here. String is massless and inextensible. And so they're going constant rate equal magnitude. So that's the big one. We're also assuming the string does not slip on the pulley so that we can use this result. So basically, as long as these things are true, it's going to be fair for us to do this crap down here. Again, as long as these sentences are true, sorry, as long as, oh my gosh, as long as these sentences are true up here, we could do this crap right here. All right, it's released from rest. Use energy methods to determine the speed after its fallen distance h. Let's just go right to the solution. Here it is. All right, okay, there's part A in detail, but here's the deal. I am going to use my trick where I have the purple coordinate system and a red coordinate system. The blocks do not have to be at the exact same height, but this is going to be y equals 0 for the red block. All right. The bottom of the motion is 0 for the red block. Similarly, the bottom of motion is 0 for the purple block, right? So one initial in the y direction is 0 at the beginning. Y final is 0 for the red block. It's a sneaky one. All right. All right. And then let's see if there's any other comments in here. This was 0 because it said so. It was at rest. All right. Since block is moving upwards, its initial height is 0. I kind of talked about that. 2 is moving downwards. That's the red block. So its final height is 0. And then if you're wondering why this has no net work, let's go through all the reasons why. Woofda. Okay. Tension, internal. Tension is internal, no net work. Same thing with the other block. Okay, even though they're different tensions, they're still both internal, right? One is acting on the red block in the pulley, so that's internal. The other is acting on the purple block in the pulley. That's why they're both internal, even though different. Oh, all right, so there's that. Forces acting at the pivot do no work, right? As the pulley is not displaced. So if the pulley's not moving around, those forces can't be doing any work, and they don't do any torque either, right? So that's cool. And gravitational forces on each block we're going to handle with GPE, so we don't need to do work. By the way, just to make this painfully clear, if I could show the pulley here, y initial equals y final equals 0 for the pulley. So if you consider the pulley object 3, do you agree we could just set a third reference height right here as 0? So if you're wondering, why didn't I do gravity for the pulley? It's because it's not going up or down at all. So we're going to ignore GPE for the pulley. All right. Here's our big equation. Take a look at it. Oof, that's a lot of crap. All right. This one is going to go to 0 because initially the purple block was at height 0. It started low and goes upwards. This one is going to go to 0 because it started high and ends up falling downwards. And now we're going to get these interesting terms over here. Let me get a different color here. all three of these terms, there is your kinetic energy. Notice this one, the first term, is for the purple block translating. I use the translational kinetic energy, 1/2 mv squared, not 1/2 I omega. This one is translating. The red block is translating. So that's also going to be 1/2 mv squared. This one is the one that's rotating. And so I have to use 1/2 I omega squared. All right. Now, yeah, I'm going to mention this step right here. This is a commonly, basically, we have, let me approach it like this. Look at this equation that I'm pointing at with the blue arrow. Look at the equation with the blue arrows here. All right. Notice that it's mixed. We have an omega, which is a rotation rate, and a v, which is a translation rate. But these two are constrained by the equation v equals r omega. So why would we keep two different variables that look very different? You pick one and rewrite it. For this one, I chose to get rid of omega, right? Because if v equals r omega, omega is v divided by r. All right. So I just plug that in, and now look what you can do if you do that. You can solve for v final all by itself. The problem is gold. You're done. All right. I'm going to pause and let you digest for a second. Get a drink of water. All right. If you have a question, this would be a good time to dump it in the chat. Hopefully you're kind of following along. That would be even cooler. But definitely keep the I mean, we're still learning here, so give me questions for sure if you got them. All right. So we had basically M2 was up in the air initially, and afterwards it raised this block up, caused the purple block to be moving upwards, caused the red block to be moving downwards, and caused the pulley to be rotating. That's all that says. I use the block's gravitational energy to do all that other stuff. From there, you can solve for V final. We're good to go. Now, notice if the blocks have equal mass, it shouldn't go anywhere. The speed should be 0. If the pulley is massless, this term drops out and it matches an Atwood's machine from experience. The units look good. And if M2 is insanely large, we'd expect free fall, right? Well, if M2 is really large, this would look like M2 minus something you can't see all over M plus M2 plus something you can't really see. These two drop out, and notice you'd get just square root of 2GH. And I saw there was a chat. I'll go ahead and clear this out and get to it. Need to rotate the coordinates. You don't need to, Nick, but I think it's tremendously cleaner. And let me show you what I mean here. I think that's a good question. So we should definitely, Nick's asking about, should we rotate the coordinate system? Let me show you something and show you why I love to do that. I'm actually going to back up to with the torque methods. I think it's so much easier to see. So if I go into that solution, remember, anytime you want to do the stack the equations and add them trick, which is a great trick, we need that rotated coordinate system. So if you look here at this picture I'm trying to screen share at the top of 1052, you could imagine your string, your right hand is the coordinate system. You're following around that pulley, or your left hand. For me, left hand worked easier. Sorry, yawn. Anyways, it makes this step right here a lot easier. I'm going to pause and go back. There's a lot of chat going on, so let's see if that helped. Yeah. Okay. Yeah, it's not required, but boy, uh, if you don't do that, almost certainly there's some thinking you have to do to put in a minus sign on some parts, but not all of them. And so the issue is if you align your coordinate system all the time and just say, everything going in my problem, again, in my problem, I said, think about this, everything going this way is positive because this is going that way, this is going that way, this is going that way. If I don't do that, I have to suddenly think, wait, do I need minus signs here? Do I need minus signs here? Oh shit, do I need them over here and over here or over here? And so by doing this, man, you just reduce the amount of thinking about minus signs. And you know how it is. If you screw up one minus sign, the entire problem is botched. And I don't like that because it takes longer to grade and you get a lower grade. So yeah. All right. Yeah. Yeah, exactly. Exactly, Nick. You're exactly on it there. All right, cool. All right. So, and since I just want everybody to get all A's, so these tests are much easier to grade. Let's just everybody do perfect work. All right. That seems like a fair assumption. All right.
I have a question, and I'm just gonna,
Sure.
so I don't want to type. Is that okay?
Yeah, for it.
Okay. And this might be a hard kind of question to ask because
Try it anyways.
I'm
Go
a little
for it.
confused. So, uh, but it's a really random question. So if you have that coordinate system like you're talking about, if you change your coordinate system in any way, like so that was just the X direction you're talking about. Um, does that mean that we can't do that trick where you
Stack
uh
him and add him.
not the stack them and atom, but the where M1 you can set the reference points. That's what I'm talking
Yeah.
about.
You could
So
still
does
do
that
that
affect the
too.
reference points in any way?
You could still do that. You could set separate reference points for each block. This is an important thing to know.
Okay.
In physics energy problems, gravitational potential energy is meaningless. Changes in gravitational potential energy have meaning. So
Okay.
that's what allows us to pick different height levels because it doesn't matter where you start. All that matters is how much you've changed for each block. And if you use a different coordinate system for each block, you'll still get the correct amount of change for each block.
Okay.
And that's why you can do whatever you want with that. It's because gravitational potential energy is completely meaningless. Only thing that matters is changes in it. Um, cool.
Yeah, yeah. So that's why we can model that change in energy, even though the X direction we can still call the same. It's still going that positive. Okay.
Yes, yes. So I think in class, you might be wondering, I think I now have the full extent here. What he's saying is in question 1052, I rotated my coordinate system, but when I did 1053, I didn't rotate it. Do you see that? And it works out either way. And what I've found is when doing torque and that kind of stuff, it's better to rotate the coordinates. Yeah, who cares? I'm just going to do it this way. Yeah, I think, did that address your question, Ryan?
It did. It did. Yeah, yeah. That makes sense.
It's very weird. It's just the nuts and bolts of doing it. If you're doing torque problems, you absolutely want to do the rotated coordinates. Energy, just always call up, up.
Okay.
Yeah, very, very sneaky. All right,
Okay.
good, good, good. Right on. All right. And I think, oh, there was one more step in here. Let's go back and look at it now. So what we did was let me get my screen up. Come on. There we go. Okay. We did an energy problem to get V. From there, look how easy this is. I could do V final squared equals V initial squared plus 2A delta Y. Well, in this case, I know V initial is 0, started from rest. I know V final is this ugly equation. I know the change in height of a block is going to be h, right? And so I could get the acceleration of this thing. Piece of cake. All right. And so if you go back to the problem from the previous result, you would actually get this. If you don't believe me, take a second and do that tonight. you could see that this piece is there. And this 2GH is going to be right in here somewhere. There's the 2. There's going to be an H right here. And so you'll get AY will still have a G in it, I think. And this one probably did too. There's the G sitting out front. It'll work out. Try it. Don't believe me. Do it. All right. Okay. Blah, 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 blah. Okay. So here's some boring crap if you care about this thing. What did I say there? I think we addressed that earlier. So if you don't believe me, when you get to part D, go back and watch the video. And that was that part where I was talking about this red friction right here on the edge, blah, 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 blah. So if you want to, you can study that video later. Let's move on. All right. Take a look at 10.54. This was a question asked earlier today. Could you do a problem with a spring? You bet. Here's how you would do it. It's not that crazy. Right now, you've got a spring here. So all you're doing is exactly the same crap. There's going to be a reference level for this one because it goes up and down. Notice, whoops, the pulley does not go up and down. This block does not go up and down. So I only have one gravitational energy. All right. So if I was doing an energy problem, I don't even know what I'm looking for. I should read. Let's read this problem. 10.54. Take a second to read it. I will too. Block of mass M attached to wall, light spring. Spring is initially unstretched, so there's no spring energy. Block is attached to a hanging block. Okay, so there's one of them. This one is mass M. We're told this one has mass 3M. That's this sentence right here, 3 times the mass. Light inextensible string. Okay, they're going to accelerate at the same rate. Their motion is tied together. They have the same velocity. Pulley with negligible axial friction. Uh-oh, it doesn't say negligible mass. We have to account for it. Okay, the pulley is essentially a uniform disk. Uniform disk, 1/2 mr squared. That's what comes to mind. I'll call that mass 3 mr squared, right? That's the moment of inertia of that pulley. Oh, crap. And look, we're supposed to get the mass of the pulley. So now I know how to get the mass involved. I'm going to have to solve for mass this time. All right, that's cool. Punt released from rest. Okay, initial kinetic energies are all 0. Level surface, negligible friction. So I don't have any work done by friction. If you're curious, how would you get friction involved? Well, you just say mu is not equal to 0, and then you could do it, right? If you had a mu there, you could do this, but in this case, mu is 0. All right. When the system first reaches the equilibrium position, it's moving. Okay, equilibrium position. This is getting messy. I'm going to clear this out. Equilibrium position. You're supposed to know equilibrium means force net equals 0. All right. So if force net equals 0, well, there's going to be a block here with a 3mg. There's going to be a force upwards on it. We could call this tension 1, right? This is tension 1. This is not tension 1. This is tension 2 because it's a different side of a massive pulley. They do not have the same tension. But I do know that these two things should be equal here. So you could try and go about and figure this all out. All right. An interesting thing happens, however, at equilibrium. If it's in equilibrium, alpha is 0. And then I believe at that one point, this tension equals that tension. So T1, let me just write it this way. R1 T1 minus R2 T2 equals I alpha. If you're at equilibrium, alpha is also equal to 0. So if you're in equilib, sorry about that. If you're at equilibrium, this goes to 0, which then T1 is actually equal to T2, but only at equilibrium. So that's a special case in this problem. All right, so that will be true. Now, when the system is the acceleration of the system is 0, but the speed is not. Hopefully that makes sense, right? This thing is falling downwards, right at the equilibrium position. It's going to overshoot and keep falling, and then eventually the upwards acceleration will cause it to slow down, and then it'll bounce up and down, and it'll go bouncing up and down past equilibrium. I'm going to get that question from the chat before we grind this out. Yeah, in this problem, R1 and R2 are the same. So, yep, okay. And then I notice we're running out of time. I'm going to show you a quick look at this solution, then I want to address the next one, okay? And then we'll call it a night. Excuse me. All right, so looking at the solution really quick for this one. Whew. In this case, this shows you how you could get the equilibrium position. Now, I kind of glossed over this, but remember, in this problem, at equilibrium, that's the one case where this tension happens to equal this tension, which happens to equal this spring force. Because at equilibrium, these two balance, and then at equilibrium, these two balance, which makes then at equilibrium, these two things balance. And that's how I related the spring all the way over to this force. At equilibrium, everything's balanced. You don't need A in the equations. All the forces are balanced all the way across all the components of the system. That is, I probably should have written something in there, and maybe I should make that better. But that is this part right here. So got it. Now, once you find out the equilibrium position, that tells you how far up the block is. So this is the mass times G times the height. It's initially up in the air that far above. Why? Because the problem tells me it goes there. Now look at this one. I have 1/2 4 mass because one of the blocks is a 3, one of them's 1, and they're moving together at the same rate because they're tied together by an inextensible string. All right. This is the rotation of the pulley. This is the spring potential energy. All right. I think you can do the rest of this on your own. It's not too bad. Finally, so do that one and come back to me with questions if it doesn't make sense. This, yeah, I love these problems. I'm not going to lie to you. There's probably going to be something with weird radii in at least one of your tests. I don't know which one. So make sure you do both of these two problems, all right? So when you look at this one, the same problem. The main difference here is, you saw me allude to it. There's a radius for this one. We'll call that, it looks like that's 0. Oh, I'm running out of room here. Sorry. Okay, this one is 0.4 R. Now, for the other one, that's got a different radius. And so now the torque equation is going to get nasty. All right, because you got two different radii, and it's just going to be fun. Fun is a word I would use. Same thing in this problem. You have a different radius for each of these. One of them is a small radius, and one of them is a bigger. When you get these types of problems, this is what I want you to remember, people. They have the same rotational states. They have the same omega, they have the same theta, they have the same alpha. That is the same whether you're talking about the blue block or the green block, okay? The blue block and the green block will relate to omega and alpha just fine, but they use different radii. So this one's going to be moving slower. So I would call this V1, and this one over here would be V2. V2 should be bigger than V1. You're unraveling more cable off the larger radius, so this one's going to be moving a lot faster than the green one. And I'm going to go get that chat question really quick. Okay. Yeah, I think you got it there. And so I'm going to I'm going to just show you the solution, and maybe I'll stop the live stream there. We're going to pick up here probably next time. So let me stop